Okay, we're going to be doing chapter 4 of calculus, and we have to start with antiderivatives. We talked a bit about that in chapter 3, but it's basically the inverse of a derivative. So to take a derivative of a polynomial, like x to the power 4, you bring the 4 down and then subtract 1 from the exponent, and you get 4x to the power 3. But if you were to take the antiderivative of x to the power 4, you do something similar, except it's the opposite of that. You take whatever coefficient you have in front, in this case it's 1, and instead of multiplying it by the exponent, you divide it by the exponent plus 1. And then it's x to the power of, and then you do the exponent plus 1 instead of minus 1. And this will give you 1/5 times x to the power 5. And if you do take the derivative of this, take the phi down and subtract 1, you do get x to the power 4. So the reason why we're adding 1 to the denominator is because the new exponent, when we're taking the derivative of the new function, is the one that gets brought down. And we want to cancel that out, so we have to add 1 to the denominator as well. The other main antiderivative we learned was for trigonometric functions, and that's just the inverse of the derivative. So whatever rules you memorized, you do the opposite. So if you have cosine x, derivative would be negative sine x, but the antiderivative would be sine x because you're going backwards in that loop. Whenever you're doing an antiderivative, if it's the general antiderivative, you always have to add plus c to the end because c stands for a constant. The reason why you're doing that is because when you're taking the derivative of the new function, you get x to the power 4, let's say in this example. But when you have the plus c, when you take the derivative of that, you get 0. So honestly, you can have an infinite number of antiderivatives. 1/5 x to the power 5 plus 0, 1/5 x to the power 5 plus 1, and so on. Because whenever you take the derivative of that, you still get the original function no matter what c is. That's why you need the plus c. Sometimes a question will give you if it goes through the point 0, 0, then you know when you plug in 0 into the original function, you should get 0, and then you can solve for c. Sometimes it's not 0, 0, sometimes it's some other value, but sometimes you might be able to solve for c. That leads into indefinite integrals. So an integral is basically a function that finds the area under the curve. And if you have a curve like this and you're trying to find the area under, we talked about methods where you can use rectangles, trapezoids, and sometimes triangles if it's a straight line to find the area. But if you want the exact area, you want to take limit as n approaches infinity of whatever sum you're using. So if you're using from k equals 0 to n, you want to put the limit outside that and then do it as normal, like b minus a over n times f of b minus a over n times k plus a. So this is actually the full formula for exact area. You just take limit as n approaches infinity, but instead of writing this in the same way the entire time, we use the integral, and it's from a to b of f of x, and then there's always a dx at the end. And this is standard notation for integrals. The reason why we need the dx is because think of it like this is this part basically means limit as n approaches infinity and the sum of both combined in one. So it's basically an infinite sum. And then this is actually the height of the rectangle at a point. So the height of the rectangle is f of x because that's the value of the function, it's the height of the rectangle. And dx is the width. So if you zoom into a rectangle, you're going to have a height, but you're going to have a width that's very small because you're going to infinity, and the width therefore goes to 0. So dx just means an extremely small value. So that's why you need the dx at the end. If you have another variable, you use d of another variable. And that's the notation. Now, how does that connect to antiderivatives? Well, an antiderivative can be used to find the integral. Basically, when you're using indefinite integrals, which is not like on a specific interval, it just notated the integral symbol, then f of x dx, there's no a to b, you're finding the general antiderivative of that function. And this is usually denoted with a capital F and then X, and then don't forget the plus C at the end. So an example would be if you're trying to find the indefinite integral of 3x squared plus 2x plus 8 dx, you would take the general antiderivative of this. So we start with this. We have to do 1 over 2 plus 1 times 3 times x squared. And this is just, x squared plus 1 because you have to increase the exponent by 1. So this is 1/3 times 3, which just cancels out, and you get x to the power of 3. For the second part, you do something similar. You do 1 over, the exponent here is technically 1. So you do 1 plus 1 times 2, which is a coefficient, times x to the power of, again, 1 plus 1. So this is 1/2 times 2, or just 1. Again, it cancels out. And 1 plus 1 is 2, so x squared. And then the final part is you take the 8. It's technically x to the power of 0, so you go 1 over 0 plus 1 times 8 times x to the power of, it used to be x to the power of 0, so you add a 1 to that. And you get 1 over 1, which is just 1, times 8. And then x to the power of 0 plus 1 is just x. So these are the three terms. And you have x to the power of 3 plus x to the power of 2 plus 8x, and then plus c. Never forget the plus c. So that is the indefinite integral because it's not along any bounds. It's by itself, it's indefinite, but definite integrals have a bounds. It's from a to b of that thing. And how you calculate that is using the indefinite integral. What you basically do is, let's say we're going from 1 to 5 of 3x squared plus 2x plus 8 dx. So this is the function from earlier. You want to find the antiderivative or the integral from 1 to 5. That's a definite integral. What you're going to do is find the general antiderivative or the indefinite integral, basically. And then you have to substitute in these values. In this case, you don't need the plus c because, as I'll show you, the c just cancels out when you're dealing with definite integrals. If we do include the plus c, we could. It wouldn't really make a difference, though. The general notation for this is you draw a bar and then you go 5, 1 to show that you're trying to plug in 5, then plug in 1, and then subtract those values. Plugging in 5, we get 5 cubed, which is 125, plus 5 squared, which is 25, plus 8 times 5, which is 40, and then plus c. In this case, we're including the plus c just so I can show you that the plus c doesn't really even matter. 125 plus 25 is 150, plus 40 is 190. So 190 plus c is what you get when you plug in 5 into the indefinite integral, or the general antiderivative. And then when you plug in 1, you get 1 cubed, or 1, plus 1 squared, which is 1, plus 8 times 1, which is 8, plus c. And 1 plus 1 is 2, plus 8 is 10, so 10 plus c. And now you want to subtract them because you're finding the area from 1 to 5, so it's everything in between. You just subtract them, and you get 190 minus 10, which is 180. And then the c's cancel off, like I said, and your answer would be 180 units squared because it's an area. That is definite integrals and indefinite integrals. But there are also properties of definite integrals that we need to talk about. And there's also one more type of definite integrals with variables as their bounds that are also important to talk about. So properties of definite integrals. There's 6 main properties. The first one is that when you have an integral from b to a of f of x dx, it's equal to the negative of the integral from a to b of f of x dx. You're just gonna take the negative of it. Oh, and yes, I will go over some curve analysis once I'm done talking about chapter 4. So that's the first property. It's basically saying if you're going from, like, let's say on a curve, you're going from 5 to 2, It's the same as going negative from 2 to 5, because even though you're still going in a positive area, and that's one thing I need to talk about, you're going in the opposite direction, and that changes it. Speaking of which, when you're going under the x-axis, area under the curve becomes negative if you're going in the right direction, or from least to greatest. If you're going under the curve and from greatest to least, like from 5 to 2, for example, then area would still be positive. So that's the first property of definite integrals. The second one is a little bit of common sense, you could say. The integral from a to a of f of x dx is equal to 0. So it's just, if you have a curve, if you're going the same place, it's 0. Even though it looks like it should be the value of the function at that point, remember, that's only the height part of the rectangle. The width is dx, and it approaches 0. So height times width, height is the value of the function at that point. Width is 0, it multiplies out to 0, and your answer should be 0. Think of it like you're taking the area of a line. You can't really do that. The answer would be 0 either way. But if you were to have a rectangle with width 1 and the height some value, then it would be equal to the height. This time the width is 0, it's a line, so you can't really have a height. The third one is absolute integral of a to b of k times f of x is equal to, or dx, is equal to k times integral from a to b of f of x dx. This basically says when you have a constant in a function, you can just move it outside. If you have 3x squared in an integral, you just take it out, 3, and then x squared. Obviously, there's the dx in both cases. Another one that's pretty common, used often, is integral from a to b of f of x plus g of x is equal to, or dx is equal to integral from a to b of f of x dx plus integral from a to b of g of x dx. Basically saying when you have an integral that is the addition or subtraction, actually, this applies to subtraction as well. So I should probably put a plus or minus here. If it's an addition or subtraction of two other functions, you can separate it into two different integrals and then take the antiderivatives of each one of those. The fifth one is integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. What this is saying is if you have a curve and you have the area from a to b and the area from b to c, you can combine it into one integral. Again, it's like in geometry where you learn this segment addition postulate. You have two segments next to each other, you can add them up and you get the same value. It's basically saying something like that, except this is the calculus version of it. And finally, the sixth property is the integral from a to b of f of x dx is equal to the integral from a plus h to b plus h of f of x minus h dx. This one is probably the hardest of them all because if you don't memorize it, which I suggest you to do, but you should also know how to get to it, because there are different types of problems that involve these, and some of them aren't so straightforward. What it's basically saying is, if you have a curve like this, and you have the area from here to here, that's all well and good. But let me use a different color for this. If you move the curve x minus h, so you move it h to the right, what you need to do to the bounds is you have to add h to them. And once you do that, you get the same exact area. Obviously, this isn't very accurate, but you get the point. If you move the function, you also have to move the bounds to stay the same area. The only reason why it's b plus h and a plus h here and f of x minus h here is because in function transformations, when you're moving to the right, you do x minus h. But in normal addition of values, when you're moving to the right, you do plus h. So that's why those are different, plus and minus h. All right. Moving on. We have integrals, definite integrals with variables as bounds, and the fundamental theorem of calculus. So when you have a definite integral with a variable as a bound, a different variable generally has to be in the integral. So let's use t instead of x. What this basically is you take the antiderivative of f of t and plug in x, and then do that to a, and this is an integral with a variable bound. The reason why this is useful is the fundamental theorem of calculus, and there are two parts. The second part is something we talked about already, so I'll go through that first. It basically says if you have the integral from a to b of f of x dx, this is equal to the antiderivative of f of x at the value a minus the antiderivative of f of x at the value b. We talked about this. This is how you find a definite integral, the value of a definite integral. You just subtract the antiderivatives at those 2 points. But the first one is actually pretty interesting. When you take the derivative with respect to x, key point here, of the integral from a to x, a can be any value whatsoever, and in it is f of t dt. Know the different variables here. It has to be a different variable in here than in the variable bound, and the one in the variable bound is the one that is being differentiated. When you have this is equal to f of x, not capital F of x, the original function f of x. Basically, taking the derivative of the integral gets the function back itself, which kind of makes sense. For the integral, you need to take the antiderivative. But it doesn't work the other way around. When you take the integral of the derivative, you don't get the original function itself. You get something similar to it, but there are things that happen with constants and everything, such that it's not the exact same. You might start off with 8x, and when you take the integral of the derivative, you get 8x plus 2. It just matters what a is in that case, and other things like that. But in a problem, if you see this golden opportunity, it's equal to this function itself. And if they ask you to tell you why, say the first part of the fundamental theorem of calculus. Two more parts to chapter 4. Word problems with integrals, basically integrals as accumulator functions, and area between curves, both of which are not as easy as the previous concepts. So I'll spend some more time on them. Integrals as accumulators, it's basically applying what we learned earlier into word problems. If you say the common one is there's like a barrel of water or something and it's leaking out, and you know the rate at which it's leaking, but you don't know how much has leaked. Let's say the function r of t, the rate, is equal to 2t cubed minus 1. That's the function that tells you at the moment t what is the speed of the water leaking out. And let's say this is in liters per minute. It's going to ask you how much water leaked out in the first 5 minutes. So in this case, you take the integral, the definite integral from 0 to 5 of r of t dt. And let's say this is a of t for amount, a for amount. This, you can technically find the indefinite integral of r of t, and that would be the function you get for the amount. You can do that, but this problem is specifically asking what is the amount leak in the first 5 minutes, not what is a function to find the amount leak. honestly, if the question didn't ask you for anything, it's best to first find the function for the amount leak in case there are multiple parts, and you might need to use that function later on. This one doesn't have multiple parts. We'll just go ahead and do this. And on the way, honestly, we'll find the indefinite integral as well, because that's how we calculate it. Fundamental theorem of calculus part 2 says that we need to find the antiderivative, plug them in, and subtract. Okay, let's start finding the antiderivative. For this one, you do 1 over the exponent plus 1, so 3 plus 1, times the coefficient, times t to the power of 3 plus 1. We add 1 to the exponent. And then minus, here it's technically t to the power of 0, so you go 1 over 0 plus 1 times 1. And then times t to the power of 0 plus 1 plus c. We don't need the plus c in this case because it's a definite integral, but when you're showing your work to find the amount function, you would need that. 1 over 4 is what this fraction equals, times 2 is just 1/2, t to the power of 4, minus 1 over 0 plus 1 is just 1, times 1 is 1, times t to the power of 1. So you get 1/2 t to the power of 4 minus t to the power of 1, or just t. Plugging values in here. Oh, and plus c, but technically we're going to be plugging in values here, so we don't need it. In fact, we can go here, remove the plus c, and just write this. Then the bar, 50, as we learned earlier, that's the notation you use once you find the antiderivative and you're looking for the values at 5 and 0 to subtract them. First, plugging in 5 to the power of 4, you could use a calculator if it's a calc section, which it likely is, because it seems like an FRQ. 5 to the power of 4 is 625, divided by 2 is 312.5, minus 5, so that's for 5, and then minus, when you plug in 0, you get just 0, minus 0. So 312 minus 5 is 307.5, minus 0 is 307.5. So in 5 minutes, 307.5 liters, the units is liters, because if the rate function was in liters per minute and 5 minutes go by, this should be in 307.5 liters. That is actually a lot of water in 5 minutes. So it probably is a big barrel or like a swimming pool or something. Now, let's say there was a second part to this, and I told you before there wasn't, but in some case, they give you the same equation, and they say, we have a similar problem where it's leaking out, and R of t is equal to 2t to the power of 3 minus 1. And let's say at t equals 0, when you first notice the leak, already 10 liters were spilt out. What is the function for the amount? Well, let's look back here. This said between 0 and 5 minutes, how much water was spilt out. This is saying, what is the function for the amount spilled out? And we already kind of got that. 1/2 t to the power of 4 minus t. So a of t is equal to 1/2 t to the power of 4 minus t. Is that our answer? No, because this case is a general antiderivative, so it's plus c. However, we know one value. At 0 minutes, there's 10 liters already out. So plugging in values, we get 0 minus 0 is just 0, plus c is equal to 10. So at 0, there was 10, so c equals 10. This is an easy example because when you plug in t, all you get is 0. So in this case, you can just add a 10 to the end instead of a plus c. And that would be your amount function in this case. And that's because it's not just 1/2 t to the power 4 minus t, because at 0, there was 10 liters. If it said at 0 minutes, 0 liters was spilled out, then great. You just put 1/2 t to the power 4 minus t. But it said 10 liters were spilled. So you have to do this. Last topic for chapter 4 is area between curves, and that is by far the hardest topic, because it seems nice, but it's not just like a formula they use in all cases. You have to think about the case. You have to actually like think about it a little bit. So we have two curves like this, and you want to find the area between them. Well, you just take the integral from the bottom bound to the top bound. And if it just had something like this, that you need to find the area between, and it didn't give you the bounds, you find the intersection points, and those are your bounds. In this case, let's say it's always in the first quadrant, and you know this intersection point is at 3. You would say 0 is the bottom bound, and 3 is the top bound because that's an intersection point. If it went beyond that, you can probably figure out that the other intersection point was -1. And then you do the top function, in this case f of x, minus the bottom function g of x dx. Now, there are different cases. First of all, you see in this case, let's say it was not from 0 to 3 and it was from -1 to 3. It actually goes below the x-axis. Does that matter? Because we know area below the x-axis is negative. In this case, we can ignore anything below the x-axis. And that is because both areas would be negative and they would just cancel each other out. See, up here, there is a positive and a positive area, and you're subtracting them. Down here, there's a negative area and a negative area, and so you're subtracting them. Whenever you're dealing with area between curves, ignore the x-axis or area under the x-axis. Second part. What if you know the function has multiple intersection points, something like this? What is the area between them? Well, either you can split it into multiple integrals, which is probably the safest way to go. You could technically do absolute value of f of x minus g of x in the integral. That is not recommended, but you could technically do it. I would separate it into multiple integrals and add them up, because this also works when you have more than two curves. Let's say you have something like this, or to make it even harder, something like that. How are you going to calculate it? Well, you split it into two areas, one from here to here, and the other one from the middle section to this end. And then you calculate the separate integrals and add them together to form the total area between the curves. And one more thing is area around area with respect to y. And that's if it's a complicated function, something like this in terms of y, you basically replace x with y, and you should be able to find the same result. You can solve for the function in terms of y and write it as x, which is not recommended because you have to do things in like inverses and everything. But you could also just say if this is x equals y squared, you just do y squared in your function dy. And since there's this x equals 1, you just do is minus 1 dy and solve for that. And that's mainly it for chapter 4. If you have any questions, let me know and I'll answer them.
I have a question.
Sure.
Yeah, so when you said you can use the absolute value to find the area or like multiple intersections, would
Yeah.
it always work or are there exceptions to it?
For the absolute value, that's a good question. It most likely will work in cases when you have curves that overlap each other and there are different top curves in different areas. But to be safe, you know that splitting into multiple intersections always works. So
Right.
just to be safe, I would recommend using this method rather than absolute value.
Okay, got it. Thank you.
Any other questions? Okay, if that's the case, then I'm gonna quickly go over curve analysis in a few minutes. That's chapter 3, but just a review curve analysis. You have a curve, let's say you know the function is f of x equals x to the power of 4 minus 8x squared plus 2x plus 1. And you want to find the key points of the curve. There's two parts, first derivative and second derivative. What the first derivative tells you is when it's increasing, when it's decreasing, when it's at a maximum, and when it's at a minimum. Second derivative tells you when it's concave up, concave down, and when it's at a point of inflection. How does this work? When the first derivative is positive, and I'll make a little table so it's easier to see. So here's f of x. Here's f prime of x. And here's f double prime of x. So there's positive, negative, and I'll just remove the circle here. Positive to negative, negative to positive, and then increasing and decreasing. These are the ones I'll go, oh, well, yeah, I'll just go with these for now. But when this is positive, f of x is positive and negative, increasing, decreasing, plus to minus, minus to plus. This is the general. When f prime of x is positive, f of x is increasing. When it's negative, decreasing. When it's changing from positive to negative, it's increasing to decreasing, so it's a maximum. And then minimum here, because it's going decreasing to increasing like this. When f prime of x is increasing, f of x is concave up, and f of x is concave down when it's decreasing. Now, when f double prime of x is positive, f of x is concave up, concave down when negative, point of inflection when it's positive to negative, and point of inflection when it's negative positive. There's no distinction like there is for minimum or maximum. And then when it's increasing and decreasing, it doesn't really, we didn't learn anything about that yet. So this is a nice handy table when you're dealing with curve analysis. So I'll just keep this up for a few minutes. We won't have time to do an example on curve analysis, but basically you want to look for these, and then you can find stuff about f of x. This table might be a bit misleading, but basically it's saying that when whatever function you're looking at is one of these characteristics, f of x is what these values are. When f double prime of x is going from positive to negative, you're looking at a point of inflection for f of x. When f prime of x is increasing, you're looking at f of x is concave up. So that's basically like the way you use this table, but I feel like it's a great way to understand curve analysis. I'm just gonna darken these a bit more so people don't mistake them for anything else. That's curve analysis. I would use a number line to find out where f prime of x is positive and negative and things like that. And that's it for chapter 4 of calculus with an extra bit on curve analysis. Thank you.